Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, we're going to be covering reservoirs and specifically the outflow structures routing method in reservoirs. This is actually part 3 discussing outflow structures routing method. The previous two parts have been covered in the previous two lessons. So let's go ahead and take a look at the screen here. I've got a very basic watershed setup sketched with a subbasin, a reservoir, and a sink. We're going to focus on this reservoir element right here. Over in the method, if I select outflow structures, in part 1, we talked about everything from description down to the outlets parameter. Part 2, we talked about spillways. And in this lesson, we will finish things off by discussing dam tops all the way down through evaporation. So let's get started with that. If I go ahead and select dam tops, right now the default number is 0, but I can click up arrow and that will give me 1, 2, 3, and so on. Now up here in the Watershed Explorer, I can expand the reservoir and then expand this dam tops folder, and I see dam tops 1, 2, and 3. So that's how I can control the number 4, 5, and so on, or just decrease it down to 0 or 1. Let's go ahead and just stick with 1 for now. And if I want to actually define the dam top parameters, I'll select dam tops right up here. And now in the components editor, I have a few new fields. The dam top represents water flowing over the top of the dam. This is typically in an uncontrolled manner that might occur during a dam breach event or some sort of emergency situation. Here are the parameters for the dam top. Our two different methods are level overflow and non-level overflow. So let's talk about level overflow first. This is basically like one constant elevation of the dam. And then non-level would be a variation. We'll talk about that in just a moment. So level overflow, we have to first define the direction. So would the outflow be through the main outlet or the auxiliary outlet? Remember, if we select auxiliary outlet, then in the reservoir, we would have to define an auxiliary location. And then the method would be some sort of hydrologic element downstream of the reservoir or the reservoir itself. And then if we select one, it would have its own tailwater elevation. This is covered in part 1. All right, let's go back to our dam top parameter and the tab. And then here's the elevation here. So this is just going to be the crest elevation or the elevation above which water begins to flow. The length, this represents the length of the spillway in a sense. This is sort of treated like a broad crested spillway as far as the flow rate equation goes. So we'll just type in a number, say 100 feet is the width that the water can flow over the dam. And then this coefficient here is the last parameter. This is a discharge coefficient. It accounts for energy losses as water approaches the dam top. So this is typically a number between 2 and 3 for English units and between 1.1 and 1.66 for metric units. If I get the equation up on the screen here for the level dam top flow rate, it is the same as a broad crested spillway, and HMS says that here's the discharge coefficient, the length, and then this H head represents the elevation of the reservoir pool minus the crest elevation, which we defined right here as 250. The next method is similar, but it's called non-level outflow. So if I select that, we again have to define the auxiliary or main as the direction, and then we would provide a cross section. Instead of the dam having a single top of dam elevation, this method assumes the top of the dam elevation can be represented by a cross section with 8 section elevation pairs, and the same broad crested weir assumption is made, and the calculations for each segment of the cross section are computed by HMS. So what we'll do here to create this paired data set is we'll go up to Components, Paired Data Manager. Now for the type, we're going to select cross section and then click the new button to create a new paired data set. Type or paste in the name you want and then click create. And now down here, we can select that record we just created. I just named it dam top cross section 1 reservoir 1. To define this actual elevation versus stationing, we'll go up to our Watershed Explorer, select expand the cross section, and then click on this record that we just created. If the data source is manual, then we'll just select the units, and then in this table tab, we have our stationing and elevation. to define. We can also click the graph to make sure that the table data we entered was correct. The other data source would be a DSS file. So if we select that, we just have to specify the file name and the path name. All right, so let's go back to our reservoir, basin, reservoir, dam top 1. All right, lastly, we have that same discharge coefficient for the non-level overflow. It's the same that we entered for the level overflow. Back to our reservoir. Below dam tops, we now have pumps. So if we increase the number of pumps, we see a pump directory appear in the Watershed Explorer, and we can add or remove pumps that way. I'm just going to make it 2. These are pumps that will move water out of the reservoir pool and into the tailwater when gravity outlets alone are not sufficient. So this is a little bit different than what you may be thinking of pumps at a reservoir, specifically a hydropower plant reservoir, where pumps will actually move water from the tailwater back up into the reservoir pool, and then power is generated during the day when prices are higher. That's not what's happening here. This is pumps literally moving water from the reservoir pool into the tailwater when the elevation doesn't allow for gravity to do that using the normal outlets. Here are the pumps. So I just have 2. I'm going to go ahead and click pump 1, and then in the components editor, I now have the different parameter values I can define for that pump. It says pump 1, but this is really to be thought of as that pump group 1 and pump group 2 and so on. Because if you select pump 1, one of the main parameters here at the top here is the number of units. So you could have multiple pumps, 2, 3, 4, whatever. And that represents the number of pumps in that pump group. Now, we need to be careful because if we do select the number of pumps to be more than 1, then all the parameters for that pump that we're going to be discussing all have to be identical. If they're not identical, then you would have to create a pump 2, or I should say a pump group 2. All right, so let's go ahead and get started. The method is a head discharge pump. It's grayed out. This is the only method available to me in HMS 4.12. Next is the direction, either auxiliary or main. We already talked about that. And then number of units again, we just mentioned that. Okay, next up is the intake elevation. This is a required field. It refers to the elevation of the reservoir pool where the pump takes water in. So I'm just going to make up some numbers here. The line elevation is the highest elevation in the pressure line for the pump to the discharge point. So the intake pipe may go in and then up and then over, or in, up, over, down, over. The elevation for this line elevation is the maximum elevation, say 190. The on elevation and the off elevation are both related. This refers to the elevation of the reservoir pool where the pumps turn on and off, respectively. So in the case of on, once the water begins to rise high enough above a certain elevation, I'll say 185, then the pumps turn on. And then once they turn on and the water surface elevation in the reservoir pool decreases past a certain elevation, I'll say 180, that's when they turn off. The next 2 fields are also important and related: minimum rest and minimum pump. These are optional fields. For minimum rest, if I type in, say, 10 minutes, this is the minimum time that a pump needs to rest after it has operated. So once the pump shuts off, this minimum rest time is the minimum time the pump must remain off regardless of the water surface elevation. That water surface elevation, the pool elevation, may exceed the on elevation of what I'm saying is 185 in this situation. That's fine. The pumps will still not turn on until at least the minimum rest duration has passed. The minimum run is a similar idea. It's the minimum time a pump must run once the pump has been turned on. So for instance, if the elevation hits 185 or whatever that on elevation is, the pumps turn on, the water surface begins to drop. And even if it drops past the off elevation, the pumps will continue to pump at least until that minimum run in minutes has been achieved. So the minimum rest and minimum run operations values, they operate regardless of what the actual pool elevation is. The next field here is equipment loss. This is the energy loss between the intake and the discharge points. This includes the intake structure, the outtake structure, any major losses, minor losses, and also any head loss through the pump itself. So it just gives us a constant value to type in, I suppose. The energy loss, the equipment loss, would be a function of the flow rate, of course. So I'm not sure why it would be constant here, but I think HMS is assuming that the flow rate would be pretty much always the same or close to it. In the case of these pumps and HMS reservoirs, it's typically a low head, high flow rate situation. Speaking of which, we have our last and final parameter here for pumps. It's the head discharge curve. So we'll go ahead and define that head versus flow rate relationship by going up to components. This is a paired data manager. And then what I want to do here is select elevation discharge functions and then click new. I'll give it a name and then create. All right, and we can close that. And now I can select that pump curve that I just created. Now, to actually define the values of that pump curve, we need to go up to our paired data manager, elevation discharge functions, and then pump right here. Here's the table of this head versus flow. And there's a graph tab. And then if we also wanted to specify using a DSS file, we can do it that way by specifying the file name and path name. My only hang up with this is that the paired data manager calls it an elevation discharge when it's really a head discharge. So that head represents the head lift through the pump. So that head that you're defining in the pump curve is the head difference due to the reservoir pool elevation and the tailwater elevation, plus that equipment loss value. All right, moving on. In reservoir, the next field down is dam break. In fact, the last 4 fields that we're seeing here is all drop downs for yes or no values. So dam break, dam seepage, release, and evaporation is always a yes or no value. By default, it's no, and there's no effect. But if we select yes, then we're going to have to talk about these one at a time. First with dam break, we'll select yes, and then I'm not seeing it up here under my reservoir quite yet, but what I've learned is if I click the save button, then the dam break icon appears under that reservoir. What you can do is click on the dam break icon, and that gives us a dam break tab down here beside our reservoir tab in the components editor. And now we need to provide values for that dam break. First is the method. There's either overtop breach or piping breach. These two methods have a lot of the shared parameters. So let's just talk about overtop breach first. Again, we'll select the direction, either auxiliary or main. And then now we need to define the dimensions of the dam break itself. So this top elevation is going to be the top of the dam face. The bottom elevation would be the elevation at the bottom of the dam break opening once the breach is fully developed. The bottom width here is the next field, and I'm just going to say 75 feet. Now, I should probably mention that HMS assumes that the dam breach area is going to form a trapezoidal shape. So like 450 and 420 would be the top and the bottom of that trapezoidal shape. The bottom width right here is the bottom width of that trapezoidal shape. And then the side slope is also required to define the total geometry of that trapezoid. So the left and right slope fields here are also required. What we're going to be typing in is the number of units horizontal per 1 unit vertical. So 2 to 1 would represent 2 run to 1 rise. If I wanted it to be 1 to 1, I would just type in 1 right there like that. The next field down is the development time. This is the total time for the breach to form from the initiation until the breach reaching its full maximum size. So we'll say 6 hours for that. The next field down is the trigger method, and we have 3 options. There's elevation, duration at elevation, and specific time. So elevation is the first one. That's the simplest. If it's selected, then down below, we just type in an elevation. So we'll type in a certain elevation. Once the pool elevation actually reaches that trigger elevation, that's when the duration time begins. That's when the dam break is initiated. The next option is the duration at elevation, and we have a trigger elevation, and now we have a trigger duration. So what this means is if the water surface elevation or the pool elevation in that reservoir is at or above the trigger elevation for this trigger duration of, say, 2 hours, for instance, that's the requirements to initiate the dam break. And then the third and final trigger method is specific time. What happens here is we have fields for a trigger date and trigger time. So using this particular format, we would type in a date and time, and it's at that particular date and time that a dam break occurs. So when using this method, you have to kind of be mindful of exactly what your time period is for your simulation and when you want that dam break to begin. The last field here for dam break is progression method. So this basically defines the speed at which the dam break occurs. The first option is linear, so that just basically means the dam break increases in size at a constant rate, a linear rate over the development time, which I have at 6 hours. The next method is the sine wave method of dam break progression, and that basically means that most of the dam break occurs at the beginning, and then it kind of slows down, and less of the dam break occurs later on in that development time, sort of like a sine curve. And then the last method is user defined. So if linear and sine wave do not accurately represent the progression of the dam break, you can click user curve. And then what we would do here is define a percentage curve and assign it to this dam break. So what that looks like is I'd go to components, paired data manager, and then I want to select percentage curves and then new. Go ahead and give it a name and then create. And then now in progression curves, I can select the dam break progression for Reservoir 1 record that I just created. In the paired data manager, what that looks like is I select and expand the percentage curves and then select that paired data set I just created. For manual entry, if I click on the table tab, I now have two fields. It's percentage versus percentage. This left column here is the independent variable. This represents the percentage of the development time. So this would range from 0% all the way up to 100%. And then the percentage here on the right is the dependent variable. This represents the percentage of the dam break progression from 0% up to 100%, I believe. All right, so let's go back to our basin reservoir dam break. The other method, that was it for the progression here, but the other method is the piping breach method. And this is all the same parameters except for the piping coefficient and the piping elevation. So you go ahead and type in a piping elevation at the elevation that the piping is occurring. The overtopping breach method is caused by water overflowing the top of the dam and then erosion slowly occurring from the top down. Whereas piping breach occurs where seepage begins to erode through the dam itself, and then the dam breach occurs that way. So that's why we need to define an elevation for piping. And then this piping coefficient here is similar to the orifice flow coefficient. It represents energy lost as water moves through the opening. So I might just say 0.8 and say the 420 again. So besides these two fields, like these ones down here as well, they are already the same as the overtopping breach method. All right, so let's click on reservoirs again, scroll down to the bottom. We still have dam seepage, release, and evaporation. The dam seepage, let's go ahead and click yes, and then click save. Now we have a dam seepage icon here. We click on that, and we have inflow and outflow. So seepage can't occur through the dam face in either directions. Inflow is actually when the seepage occurs from the tailwater into the reservoir pool, and then outflow would be when the seepage is from the reservoir pool out into the tailwater. Let's go ahead and define the paired data set for that as an example. I'll go up to components, paired data manager. For the data type, I'm going to say elevation discharge. Now this is the one we already defined for pump. We want a different one. So I'm going to call this seepage for reservoir 1. There it is. And then now I should be able to select seepage for reservoir 1. I could select the same for both inflow and outflow seepage, or I could select and define a separate paired data set to represent the elevation versus discharge, seepage inflow and outflow separately. Let's go back to our reservoir here. Select that. Next up is the release. So if I say yes to release, this is for additional releases. If I click save, I now have a icon here for additional releases. This is releases in addition to what we've already defined: outlets, spillways, dam tops, pumps, breaks, and seepage. If there's some other sort of release that needs to be quantified, then this is how we do it. We say releases, yes. Click on the additional release icon here. It brings us an additional release tab in the components editor. And now we just need to define a time series for that release. So what we do to do that is we go components, time series data manager. We want to select the discharge gauges method or type. So that's the second one down here, discharge gauges, new, give it a name. And additional discharge is what I'll call it. And then I will select that additional discharge or reservoir 1 time series dataset. In the Watershed Explorer, we can define what that exact data is. So I would expand my discharge gauges, select the additional discharge reservoir one, the time series data set I just created, and then define the data right here. Now I'm in US customary units, so I'm going to change the units to CFS. For some reason, it was CMS. And then if it's manual entry, then all I'd have to do is select the interval and then come up here and select the default time window that it's provided me. This default is the first day of the year 2000. And if I want a different day, and I probably would, I would just change those values right here. If I wanted multiple time windows, I can create additional time windows like that. Just right click on the paired data set, right click, create time window. And then to actually add data, we would go ahead and select on that time window and then the table value and then type in or paste in the actual additional outflows that we want that reservoir to exhibit during the simulation. So it's important to make sure that your time window is consistent with the simulation time window. Another way to define that additional discharge is to select a DSS record or multiple DSS records or files from the data source. So if you do that, you would just have to specify the file name and the path name. All right, back to reservoirs. And then the last parameter here is evaporation. So let's go ahead and click yes, and then click save, and then click on our evaporation icon here in the Watershed Explorer. We have one method, it's called monthly evaporation. So what we would do here is just type in a number of inches of evaporation that occurs from the reservoir in each month of the year. When you're using this evaporation method, the reservoir also needs to have used the storage method elevation area. Can't go with elevation storage because we need to know what the area is, because for the evaporation volume to be calculated, it's really this depth that we're defining each month times the area, which would give us a volume. So that volume would be removed from HMS. It would not contribute to either the main outflow or the auxiliary outflow. Well, that's it for this lesson in outflow structures routing. What we talked about were the parameters from dam top down to evaporation here in part 3. In parts 1 and 2, we talked about the other parameters as well. And taking a step back, we are defining the properties of a reservoir in HEC HMS, which uses this outflow structures routing method.